All right, folks, part 2 of your molecular geometry video going over VSEPR shapes, bond angles, names of the shapes, and polarity. Watch part 1 for the first 4 examples. I'm going to do another set of examples in this video, a little trickier, but pretty much the same thing. I'll do one at the end that's a little more complicated that has multiple central atoms, but before that it's kind of just more of the same from part 1. So we're going to start out with this example here, C2H4, and I guess this one could be a little bit tricky because we have more than one central atom, even though they're the same. So when we look at this one, when we're determining the shape, there are kind of 2 central atoms, so we really have to look at both of them, but they end up being the same. So if we consider this carbon here first, remember, we're going to use this handout to figure out the shape. So we want to count the electron domains around this carbon. So there's one there, and one there. So the carbon here has 3 electron domains. So we go to 3, and all 3 of them are bonding, right? There are no lone pairs. Carbon doesn't like to have dots. So none of them are bonding, which brings us to the shape trigonal planar, with bond angle of 120 degrees. And before I draw this, let's also look at this carbon. It has also 3 electron domains with no lone pairs. So it has 3, 3. It is also trigonal planar. So these carbons are identical and they're both trigonal planar. So when we draw it, we need to make sure that it looks like this. Trigonal planar means that all 3 of the bonds are getting as far away from each other as possible with 120 degree bond angles. So we need to show that when we draw it. So here I'm going to start with the carbons in the center, and then to get that trigonal planar shape, we need to make sure that the hydrogens go in this direction like that. These are all hydrogens, like that. And the bond angle would be 120. And this is called trigonal planar. And since it's the same for both, you don't have to specify. It says with respect to either one of these carbons, the shape is trigonal planar. Okay, and we have that here. You can see this trigonal planar shape. The double bond ends up looking very similar to the drawing. Okay. When we think about polarity for this one, it's a little bit tricky since there are 2 central atoms. You can kind of think about the 2 carbons here, since they're both carbon, think about them as a central atom together. So when we ask our 2 questions about polarity, think about the 2 carbons as the central atom. So are there lone pairs on the central atom, or the central atoms? So there are no lone pairs on these 2 carbons. And is the central atom bonded to different elements? Well, the 2 carbons here, all they're bonded to are hydrogens. So since there's no lone pairs, it's all hydrogens around them, this is actually non-polar. It's very balanced and symmetrical on all sides. Okay, so this is a non-polar molecule. A little bit tricky. Alright, so that's the first example for this video. Do a few more. I'm going to switch to a new page. Second half of the assignment, we're going to do ozone, O3, this one. Okay, so we have the Lewis structure done already. We need to figure out the shape by counting the electron domains. So we're looking at the central atom. We see an electron domain here. Remember, a double bond counts as 1 electron domain. We have a lone pair here and a single bond there. So total we have 3 electron domains. So we'll get a 3. And of those 3, 2 of them are bonding. And 1 of them is non-bonding. 1 of them is a lone pair. That leads us to bent, which we saw in the last video, but this is a different type of bent. It has a different bond angle. So this bent, we draw it the same way, but notice that the bond angle is now 119. It's a larger bond angle, and I'll show you with the model kits why that is. So when we draw it, we'll draw it the same way. Remember, you need to show the double bond, but you do not show the lone pairs. So that is the shape. It is also called bent. The bond angle is different though, about 119 degrees. Okay, so it's a little bit less than 120 degrees. So we have this shape here. Remember, the blue thing is the lone pair of electrons. So this bent is different than this bent. And when you look at the model kit, you can see why. This one here that we just drew, the ozone, only has one lone pair on the central atom. This bent has two lone pairs on the central atom. So that's why this is a smaller bond angle. This is a 104.5 bond angle. This is a 119. Okay, so you can see the difference in those two bents. This 119 bond angle is closer to the one we just did for trigonal planar. Okay, because the only difference here is that instead of the hydrogen, you replaced it with a lone pair. So that lone pair is going to push these bonds closer together to make this angle smaller. Okay. And then polarity, we look at our Lewis structure and ask, do we have lone pairs on the central atom? Yes, we do. Since we answered yes, we know it's polar. Remember, if it's yes to either of those questions, then the molecule is polar. Since there are lone pairs, this molecule is polar. Okay. Next, we've got PO3 minus. So let's look at our electron domains. On the central atom, one there, one there, one there. We've got 3 electron domains. Okay. So we've got 3 electron domains. 3 of them are bonding, all 3 of them. None of them are lone pairs, which leads us to trigonal planar. Our old pal trigonal planar. So remember, we draw it like this with all of the bond angles as far away from each other as they can be. So we'll put P in the middle, and then we'll have, you can draw this going up or down, whatever you want. So just to be different here, I'll have it going down this time. Okay, so there's the shape with the trigonal planar, bond angles of 120 degrees. Okay, and the reason I wanted to go over this one is when we consider the polarity. When we ask the 2 questions, we look at the Lewis structure. Are there lone pairs on the central atom? No, there are no dots on the phosphorus. So the second question is the central atom bonded to different elements? No, they're all oxygen. So since we answered no to both of those questions, this molecule is non-polar. It is completely balanced and symmetrical. So some of you might be wondering, how is that possible when that double bond is different than the single bonds? Well, it has to do with resonance. So remember, resonance structures, when we're drawing this Lewis structure, you had a choice where to put that double bond. And in this particular molecule, it didn't matter where you put the double bond because all of the oxygens are identical. So you would have had 3 different resonance structures where the double bond could exist here, here, or here. In reality, it's not like the double bond is jumping around. It is actually somewhere between a single and a double bond. So really, all 3 of these bonds are like between a single and double bond. They're all the same strength, all the same length. So this is just one picture of how we could draw it, but really all the bonds are equal, and this is a non-polar molecule. So when I have the model here, this isn't the most accurate representation because this looks like there's a double bond here and then single bonds here, but really all of the bonds are the same. Okay, so it's a little bit tricky, that concept, but since we have all oxygens here, there are no lone pairs. This is a non-polar molecule, so you'll see examples like that sometimes. Okay. And the last one. This one's a big one. So we've got HC2H3O2. Hopefully, or maybe I've done this, I usually give the formula a little bit differently, because if you write it this way, CH3COOH, it is giving you hints as to how this compound is bonded. So if you write it like this, it tells you that these 3 hydrogens are bonded to that carbon, and then these oxygens are bonded to that carbon, the hydrogen is bonded to the oxygen, and then the carbons are bonded to each other. So I kind of like to write it this way because it shows how to draw the Lewis structure. Once you have the Lewis structure, now we have to figure out what the shape is, and here it's confusing because there are a lot of shapes. You could look at this as a central atom, or this, or this. For the homework assignment, it's asking you to get the shapes for this carbon, the one with 3 hydrogens, and for the other carbon, this carbon here. You don't have to get this shape, but we will talk about it. So let's look at this carbon first. So just take it one central atom at a time. I know it looks big, but just look at this one. Do the same thing you did for all the others. Figure out how many electron domains. So there are 4 electron domains for this one, 4 electron domains, and all 4 of them are bonding. So we'll go here. None of them are non-bonding. There are no dots on this carbon. So this shape for that carbon is tetrahedral, 109.5 bond angles. And remember that we draw it like this, 1 going up, 3 going down. We might have to alter that a little bit, so we'll see how to best draw this. I'll see how this goes. So I'm going to have this hydrogen here. Hopefully this turns out okay. Oh, see, I already messed up. This should be a carbon, right? Because it's bonded to a carbon. I almost wrote hydrogen. Okay, so we've got that carbon has a tetrahedral shape. So those bond angles are 109.5. Okay, so this one is tetrahedral. Now let's tackle this carbon. So we've circled that as an electron domain. Here's another. Here's another. This carbon only has 3 electron domains around it. So we'll go to 3. All 3 of them are bonding. Carbon does not like to have dots, just likes bonds. None of them are dots. So this carbon here has the shape trigonal planar. And remember, to draw that one, we draw the 3 bonds as far away from each other as possible. So let's think about how we can draw this one. Okay, so I can put the double bonded oxygen, since I already have a bond going this way, I can put the double bonded oxygen here, and then I can make this bond go up to the other oxygen. Okay, and then from there, again, you'll need to figure out how to draw this, but let's fill out what we have here. This is trigonal planar. Okay, and let's just do the shape for this one too. You don't have to write the name, but you do have to draw it. So this oxygen here could also be a central atom. It has 4 electron domains, and 2 of them are bonding, and 2 of them are non-bonding. So this is a bent shape. So draw it like this. So I already have one arm going this way, so I can make the other one bend that way, and then so this would be bond angles of 104.5. This one here is 120. So 120 for this, 109.5 for these, 104.5 for those. It doesn't ask, but just so you are aware. And we do have this one built here. It's crazy looking model. So you can see if we cover these, you can see the tetrahedral shape. Okay, so that's this carbon here. And then we have our trigonal planar carbon, if you look there, right? Double bond to oxygen. And then this oxygen has a bent shape, which you can see there with the 2 lone pairs. Okay, so 3 different shapes make up this big molecule. And when it comes to polarity, when you're asking is it polar or nonpolar, just look at it. Is it balanced and symmetrical? You can look at your drawings too. It is very different on all sides. So this is clearly a polar molecule because all the sides are different. And I will just say that the bigger the molecules get, when you're drawing larger Lewis structures, the harder it is for them to be nonpolar. Because remember, nonpolar means it's very symmetrical and balanced. So when you get really big ones, it will almost always be polar. Okay, so something like this. Very busy, lots going on, and very different on all sides. Okay, so those are a few examples, quite a few examples from your molecular geometry homework. So hopefully that helps you in determining the VSEPR shapes and polarity. Good luck.